Hello everyone. Our paper's title is MULLS Versatile LIDAR SLAM via Multimetric Linear Least Square. I am Yue Pan, a master student from ETH Zurich. This work is done with engineers and researchers from Herside Technology and EPFL. The rapid development of autonomous driving and mobile robots calls for off-the-shelf 3D LiDAR SLAM solutions that are adaptive to LiDARs of different specifications on various scenarios. To design such a system, we need to use a scanline-independent representation of the LiDAR frame. The ring and range image representation is closely related to the scanline geometry of the LiDAR model, and only the row point cloud does not depend on the LiDAR's specification. Besides, we should guarantee the observability and robustness of the LiDAR's lens system for the challenging featureless and dynamic environments. To this end, we propose MULLS, a scanline-independent LiDAR SLAM system with low drift and real-time performance for various LiDAR and scenarios. In front-end, MULLS jointly optimizes the point-to-point, point-to-plane, and point-to-lane arrow among various feature correspondence using linear least square for efficient transformation estimation. Besides, we adopt the novel T-cell algorithm for the fast and certifiable global registration and loop closure in backend. MULLS ranks among the top LiDAR-only SLAM systems on KITTI dataset. We also make MULLS open source. As the vital operation of LiDAR SLAM, point cloud registration can be categorized into local and global registration. Local registration requires good transformation initial guess to finely align two scans and is often used for LiDAR odometry, while the scan-to-scan transformation is relatively small. The most popular algorithm for this job is the ICP algorithm. Classic ICP gives alternatively sloping for dense closest point correspondences and rigid transformation. To guarantee real-time performance for LiDAR odometry, sparse variants of ICP have been proposed for SLAM applications in recent years. For example, long and LiGo-long extracts sparse ground, edge, and surface points. ICP is applied within each point class, and the transformation estimation is solved by a nonlinear optimization. To speed up, these methods usually uses ring or range image representation, which depends on specific LiDAR model. On the other hand, global registration can closely align two-point clouds regardless of their relative pose and is used for loop closure and constraint construction. Ransack-based matching and verification is often used for 6-degree of freedom transformation estimation, but is not efficient. In MULLS, we make several improvements of the previous work to make the system work efficiently for various LiDAR and scenarios. For the front end, we avoid using scalar information and extract the richer feature points such as facade, roof, pillar, and beam. The nonlinear optimization is replaced by a linear least square. For the back end, Ransack is replaced by the more efficient T-cell algorithm. Now, I'd like to introduce the proposed MULLS SLAM in detail. For each LiDAR frame, once the point cloud is collected, the sparse geometric feature points are extracted from it. As the preprocessing step, motion compensation is initially done with the uniform motion assumption using the transformation estimate from last frame. Next, the undistorted point clouds are classified into ground and non-ground points. This is done by dual threshold ground filtering in 2 degrees. The normal vector of ground points and further estimated using Ransack-based plan fitting. Then, PCA is done in the neighborhood of each non-ground point. Non-ground points are classified into facade, roof, pillar, beam, and vertex points according to the neighborhood, linearity, planarity, curvature, and eigenvectors direction resulting from PCA. For each vertex point, we count the feature points of each other categories in its neighborhood. Together with the normalized intensity and height, we encode the lightweight neighborhood category context, namely NCC feature, for the vertex points and use them for global registration in backend. Once the feature points are extracted, we can conduct the registration. Take the scan-to-map registration as an example. We only consider the geometric feature points in current frame and the local map. The transformation is estimated for each frame and applied on the feature point. The transformed feature points are then appended to the local map to keep it updated. Firstly, the closest point correspondence is determined in each class with the normal and primary direction consistency check. Next, the multi-metric transformation estimation is conducted. We'd like to find the transformation that minimizes the total sum of square of the point-to-point, point-to-plane, and point-to-land distances. This distance can be calculated as the norm of the residue. The residue dot product the normal vector, and the residue cross product the primary vector, respectively. On the tiny angle assumption, the rotation metric R can be represented linearly with regards to the ruler angles. Regarding the unknown parameter vector as Cauchy equal to Tx, Ty, Tz, alpha, beta, gamma, we can formulate the minimization as a linearly squared problem. The overall design metric A and observation vector B can be calculated and assigned. Each point-to-plane correspondence contributes to one row of A metric and B vector, while each point-to-land and point-to-point correspondence contributes to 3 rows. Cauchy is then calculated as ATPA's inverse times ATPB, while P is the weight metric. The weight metric is defined as a diagonal metric with the correspondence-wise weight on its diagonal. We use a multi-strategy weighting function, which is the product of the robust residue weight, directional balanced weight, and the intensity consistency weight. The registration quality can also be evaluated using different indexes such as the posterior standard deviation, the information metric, and the non-ground overlapping ratio. This index would be used as the weight of the backend postgraph optimization. In the front end, along with the registration module, a local map containing static feature points from the history of frames is maintained with a fixed radius from current frame. For the backend, the local map is periodically saved as the submap, which acts as the processing unit. The candidate loop closure edges among the submaps are constructed and verified by the certificated and fast teaser global registration algorithm. The initial correspondences are determined according to the cosine similarity of the NCC features encoded during the feature point extraction module. Teaser is able to select the true positive correspondences and estimate their transformation. Taking Teaser's estimation as the initial guess, the map-to-map MULLS ICP is applied to refine the intercept map edges. Once a loop closure edge is added, the post-correction of free submap nodes is achieved by the intercept map postgraph optimization. After mapping mission is completed, the inner submap PGO is done to each submap by fixing each submap's reference frame and adjusts the other frame's pose. The proposed MULLS system is evaluated on KITTI, BMAP, and Hersight size, covering various outdoor and indoor scenes using 7 different types of LiDAR. On the slide, we show the trajectory and the constructed map of MULLS on KITTI dataset. For the revisited region, the point cloud is consistent without ghosting. For the featureless and dynamic highway sequence, we can hardly distinguish the estimate trajectory from the ground truth, and there's only a land level drift in the end. In this table, we compare the proposed MULLS SLAM and MULLS LO, the version with loop closure correction, with 10 state-of-the-art LIDAR SLAM systems. The average translation and rotation error, namely ATE and ARE, are used for localization accuracy evaluation. The red and blue fonts denote the first and second place of the accuracy on each sequence, respectively. Some variants of MULLS are also compared in the table. Define an iteration as the full process of close point association, linear least square transformation estimation, and source point cloud updating during registration. M1 means apply scan to map registration for only one iteration, while MC means do scan to map registration till convergence. From the experiment results, we can see that MULLS outperforms SOTA LiDAR, LO, or SLAM methods with an average ATE equal to 0.49%. MULLS surpasses the roundup by about 30% on highway sequences. And compared with the variants of MULLS, we see that with only one iteration, MULLS N1 has comparable performance to SOTA systems. And with 5 iterations, MULLS N5 gets average ATE of about 0.6%, which is close to the converged MULLS with about 15 iterations. We can see that we can sacrifice a bit of accuracy for faster operation for MULLS. In addition, we run MULLS on 2 more datasets collected by 6 different LiDAR. The results of the consistent map used by MULLS SLAM on Hillside dataset indicate MULLS' ability to adapting to LiDAR with different specifications in both indoor and outdoor environments. For MIMAP dataset, a 5-floor building is mapped by MULLS. The main differences between the millimeter accuracy TLS point cloud and the map generated by MULLS is only about 6.7 centimeter. Furthermore, performance evaluation on the adopted categories of geometric feature points and the weighting strategy are conducted to verify the proposed method's effectiveness. We can see that the ground plus facade plus pillar is the best selection for urban sequences, and bin is necessary for highway sequences. It is also shown that vertex point-to-point correspondence undermine LO's accuracy, because they often lay on unstable high curvature points on bridge stations. As for the weighting strategy, it is shown that all the 3 strategies are proven effective on both sequences, and the translation estimation has obvious improvement on featureless highway scenes with the consideration of intensity consistency. Finally, we examine the runtime of MULLS. Experiments on various datasets indicate that MULLS is guaranteed to perform in real time on a moderate PC. Specifically, the consuming time is proportional to the point number, and the transformation estimation costs only 0.2 milliseconds per iteration, and the time is mainly consumed on feature point extraction and the closest point association from the unordered point set. To conclude, in this research, we propose MULLS, a scanline-independent LiDAR SLAM system that works for various LiDAR and scenarios. For the first time, we devised a linearly square solution to the joint optimization of point-to-point, plan, and land arrow, and apply teaser on loop closure. Besides, we have made MULLS implementation free available online. Thanks for your attention.